So thank you, Sabine, and thank you, Joe, for inviting me today. And thanks, Sabine, for these kind words that are, as usual with Sabine, they're always super kind with everyone. So, but anyway, so today what I'm going to do is I'm going to talk about landscape dynamics and the way we have been developing tools to facilitate our understanding of how Earth surfaces have been impacting different environment, but also the biodiversity and potentially, if I've got time, it depends when I know we have to go for dinner, but if we have time, I will also try to talk about something which is not going to be global. I will start with a global thing, but after, if we've got time, I will try to tailor it more to a kind of Australian kind of story, okay? So let's start. And I know that most of you guys knows about it, but basically the Earth surface processes or the Earth topography, so the high and lows in the elevation, basically they are the product of ongoing battle between tectonic processes, okay, and surface processes. And so surface processes, they will be triggered by climates, so ice, water, rain, and these surface processes are going to erode the surface, create some landscape, and transport sediments from what usually I will call the source, which is like these mountains, okay, or steep region towards the ocean and or towards sedimentary basins, which can be in continental places. Okay, so here you've got kind of two different expressions of this surface processes and how basically they will impact the Earth surface. So that's like really like two extreme version of it. When we think about landscape, and I will start this analogy with the human body here, and I will come back to it at some stage. Usually when we talk about the surface, we like to think about it as a living skin of our planet, okay? Because it's at the interaction between what is happening inside the Earth, okay? So the geosphere, what is happening at the surface, but also the impact of the atmosphere on it, okay? And it's at the junction between these different spheres and also the biosphere, okay? So I like to think about it as the living skin of our planet. And in many cases, in many applications, especially when you start to look at really deep time, so over like, several tens or hundreds of millions of years, usually people will consider this landscape as relatively steady, okay? And not just like the general public, but even like scientists, for example, if we look at people who are using climate models, okay, they will have a kind of representation of the landscape that is not really moving, okay? And this is quite funny to think about it because we know that landscapes are really transient, okay? They are going to quickly change. And we've got an example of that, like if we look just over the last years, the number of flooding events, the number of landslides that we saw on the news in different places around the world. So we know that these landscapes, they are moving fast, quickly, okay? So really our idea was to try to integrate some of this dynamic of the surface in other kind of disciplines, such as how can we integrate this, for example, in climate science, or we can use that, if we are looking at biodiversity, and try to develop some tools to be able to improve on these things. And I think that's one of the last slides of my introduction, but I could not have started this thing without talking and without showing a kind of an image from an illustration that was made in 1841 by Alexander von Humboldt, who was really like the precursor and really the guy who paved the way for many others. I think Darwin or Wallace, they had the books of Alexander von Humboldt when they started their journey around the world. And basically, he looked at the interaction between nature, so different species, how it connected to change in the landscape, but also to change in the kind of stratigraphies that you find. And he tried to relate that together. Okay, so he had this idea of trying to have a cross-disciplinary view on the evolution of the Earth. So at the today, of course, since then, there has been a lot of progress that have been done, but this interaction and this complexity between the different components, they remain elusive in many aspects, okay? And we are going to talk about that a bit today. But overall, this idea of looking at the landscape, basically, it helps us to answer some questions. For example, how does the planet regulate its own climate? And for example, like the impact of weathering on the regulation of the carbon cycle. Why there is some places on Earth which have a huge biodiversity and others which have no, pretty or nearly none. How did the surface environments basically drove the evolution of life, if it did drove the evolution of life? Okay, so what are these kind of questions, which are important questions that potentially we can try to solve with this kind of models. So I've got like 3 different sections in this talk. So I will start. The 2 first ones are related to basically this science paper that Sabine was talking about. And then after I've got another one. So I will start with the first one, which is like, can we improve our understanding of past surface and past past geographies using these numerical models, and to try to do that in a relatively in a quantitative way. So instead of just not just, but instead of using data or observations that we find from the field, is there a way to test some hypotheses that have been made based on this data? So I don't know if you can see that. I'm not like, so there is many other colleagues that works with me. Some of them are present here. And so this is like, of course, a collaborative work. So if we think about the past landscape, usually what people have been doing is trying to infer from like either present day analogs. So you will look at how the landscape is distributed at present, and you will try to understand how it might have changed in the geological time. Of course, you can rely on plate reconstruction and on the many numbers of data sets that exist, from wells to fossil records. So here you've got 2 examples, one where Sabine was a part of the study, which was a work that was done by a former PhD student at Sydney Uni, Wen Chao, where basically you can see the representation of the geographies, okay, over the past, is basically mapped relatively simplistically, I would say, with, for example, regions that correspond to mountains, regions that correspond to relatively flat landscapes, and then after some shelves, okay? And how these things are moving over time. And so that's one way of looking at it. Another way, which is relatively similar, except that they draw some rivers in different places, but basically it takes the same idea of looking at what we observe, what are the geological records, and try to reconstruct based on that an idea of the evolution of the surface. Okay. So one of the problems that we have with such model is like it's difficult to assess quantitatively how these models perform. So we end up with many different reconstruction, okay? And to tell which model is better than the other, it's a tricky question, okay? So our idea was to try to develop a technique that will help us to evaluate which model was performing better than the other, better than another one in a specific region, okay, or during a specific period, right? Or was there any of the old models, all the paleogeography reconstructions that you can find? Is there any time interval in the geological records where all these basically paleogeographies, they come with an agreement, all right? So to do that, we decided to look at the surface processes, because the landscape is basically the results of these processes. Okay, so the idea is that you can, for example, use some paleoclimate models. Okay, so a distribution, for example, of rainfall over time. You can use some of these paleogeography models. You can impose some tectonics, so it can be plate tectonics, can be, I don't know, dynamic topography. You combine them together, okay, and you look at the product of these two and at the expressions that it will left on your surface, okay? So here you've got, based on these two forcing, you get kind of erosion deposition maps, okay? And this erosion deposition map is going to evolve over time, and also it will basically drive the evolution of your surface. So to do that, we develop a tool which is open source tool. Maybe it's not as easy to use than the previous one that we developed. And really, like the main difference between this model and the previous model that we developed, which was called Badlands, this one is called Gospel. Nothing to do with the Vatican. No, Gospel standing for GoSPL, SPL being the stream power law, which is the law that we use to describe the erosion by rivers. Okay, but and I'm reassuring you right now, this is the only equation that I've put, and so it should be fine for the entire thing. But here you've got a kind of an example of the website that gives you some ideas about, you know, the approach that we use, but also some kind of user guide. But basically, the idea is that the change in elevation is controlled by uplift, okay? So uplift or subsidence, sorry, tectonic processes. It's controlled by the amount of erosion or deposition that you will get, which can be dependent on two processes in our model. So that's really a simple model in its sense. It's the kind of equations that have been put in place 20 years ago, okay, where you've got two processes that you can account for. The first one, I will start with this one, the simple one, the hill slope processes, which is basically gravity driven, okay? So you don't need to have water or anything that is flowing on the surface. By gravity, if you've got a slope over geological timescales, so 1,000 to 10,000 of years, this soil that you've got at the surface start to slide, okay, due to gravity. The second process is like rivers-driven processes. So you can have either erosion or deposition, depending on the capacity of your river to transport sediments, or first erode them and transport them. So to do that, we use what is called a stream power law, which is basically you are going to scale the amount of erosion based on the slope and on the amount of water which is flowing at the surface. Okay, so that's really a simple model. So really, like really the main difference between this model and most of the models that you will find is our ability to solve this kind of equation at global scale. Okay, and to do that, there is two different technical challenges that we had to solve. First one was to be able to run these models on supercomputers. Okay, so basically the models that I'm going to show you, and I think like most of the images I'm going to show you, they have been run on 100, 150 cores, okay? And I think they will represent about 10 years of simulation. So if we think about, the amount of CO2 that comes out of these models, this is massive, okay? We are talking about someone like leaving his computer, Sabine's one, not mine, for 10 years running, okay? But so that's the first challenges that we had to solve. The second one was our idea was to look at the evolution of this landscape, not over 10,000, 100,000 years, but to look at millions, 10 millions, 100 million years. Okay. So to do that, we had to implement ways of solving this system of equation in a stable way. So to do that, to avoid having any numerical instabilities in our model, we had to basically use a kind of implicit approach to do that. So there was a bit of a thing to do that. But basically, that's the main two difference between standard model and this one. So as other models, basically you have that's our model, okay? And what you will feed it with is some elevation, some climate, some tectonics. So the idea is that here I'm going to present some models which are based on Scotty's paleoelevation, on a specific type of rainfall, paleoclimate models. But the model is completely agnostic of that. If you've got another plate reconstruction, if you want to test another paleoclimate, you can, okay? Then after, from the model, what we end up with is a kind of a description of the dynamics of the landscape. Okay, that was why we designed the tool initially. And then after, you've got also some information about, for example, the stratigraphy, the fluxes of water and sediments across the continents and in the oceans. And also, like, you can track potentially where your sediment is coming from and where it ends up. And so after, what you can do is you can look at your outputs and compare that with empirical data as we do routinely. Okay. So here is the kind of output that we generate here for two specific time steps. One at 155 million years ago. This one at 11 million years ago. Okay. These models are run globally. And the resolution that we've got is the resolution that we set initially in this kind of model is about 5 kilometers. Okay, so we've got a global reconstruction at 5 kilometer resolution. The idea of using a resolution which is quite high, if we think about, we are talking about 0.005 degrees in terms of cell resolution. The idea was to reach this kind of resolution to be able to really try to infer the evolution of the landforms on this landscape. If we had something that was too coarse, the advantages compared to simple models that just represent like a smooth idea of the landscape will not be really relevant, okay? So the idea was to be able to really try to tip into this kind of super high resolution model. So you've got, so here it's just like closer view of the model. So you've got the elevation here, and you've got superimposed to it the drainage networks with some places where you've got some of the water which is basically going into like enclosed basin where you form some lakes, and this water, depending on the flux of water, will be able to flow down to the coast, or maybe just like stay in these lakes. So you've got these things, and of course, what you record as well is the change in erosion deposition. So we can look at the rate of erosion, but also the rate of deposition. So here in purplish, you've got the erosion rate. Okay, is it rate? Yeah, rate. And you've got in orange, really good choice of colors. In orange here, we've got some sediment accumulation. Okay, so you can have sediment accumulation in continental basins, as well as some sediments that will end up within the ocean. Okay. So to give you an idea of what is the difference in terms of what we obtain for like the landform features compared to a traditional paleogeography model. Okay. Here I put the Scotty's and Wright 2018 paleoelevation. Okay. So you can see it's already like one of the highest resolution paleogeography models that you will find on the market. I'm not saying that it's the best one. I hear a lot of people in my school saying that it's a nonsense, this one, but that's okay, because it's not really our problem. I mean, at least not my problem. And this is the result from the model. Okay, so you see really the difference between the two. What our model is able to do here is really to describe a complexity within the landscape. Okay, we are able to, for example, if I'm just looking, this is the Andes. I can look here, this is something relatively smooth. what I can have is I can have in my model basically some insights valleys that are going to change over time. And this insights valley and the rivers that are going to form in these valleys, they are going to transport sediments that I can track where this sediment is going. Does it stop and end up in an alluvial plain? Does it move towards the ocean? Okay. And so the idea is that what I've got here is a quantitative tool, okay, to test this reconstruction. I said, okay, let's say this reconstruction is true. All right. Let's run a model. Let's look at what I end up with in terms of landforms, in terms of sediment flux, in terms of stratigraphy. Can I find the same thing, and can I observe the same thing at present day? Okay, and I'm going to show you that just after. So what we end up with, okay, I just already showed you that, is basically a global reconstruction of the stratigraphy. Okay, and here I just made a cross section in the middle here with the Amazon fan. So that's 20. That's the equator up to 20 degrees north latitude. And so I've got like a globe with all the sedimentary records that is deposited based on the input I've got. So basically, if I'm using the paleogeography from Scotties and some paleoclimate model associated with this paleogeography, I should end up, based on the model, with, for example, a thickness for this Amazon fan, or I don't know, 20 kilometers or something. Okay, does it make sense? Okay, if I look at seismic, I look at some of these large deltas. Okay, do I end up with something that is similar to that? All right. So that's the first way that where you can use this model to compare what you end up with in terms of output from your result, from your simulation with some observation. And so we did that in this science paper, and I'm not going to enter too much into the details here, but basically you can slice the globe in any places and look at your stratigraphic architecture. You can compare your stratigraphic architecture with some seismic line, as I was saying. And here is another example. And basically look for places where your model is predicting something that doesn't make sense compared to the observation. And here is a nice example. So we are, this is a cross-section 3. So we are crossing here on the southern part of South America. And there is two basins. In this place, there is a Salado Basin and the East Colorado Basin. And in the middle here, at present day, we've got a kind of a small mountain range, which is called the Tandilla system. And if I compare basically the history of feeding of these two basins with what I've got from my models, I see that my model is predicting that initially I've got like a kind of a large basin, which is filled with sediment. And at some stage, I've got a kind of a surrection, which is uplifting the center of this basin, creating like this kind of two mini basins that are, not maybe mini, but two basins that are filled with sediment. So there is some differences between what the model is predicting and what I can observe. So here, I've got two options. Is either I can say, okay, so maybe there is processes in my model that I don't consider that are really important. So that will be a first option. Me, I will go for the second option, is my inputs. So the work that others have done is basically not accurate enough. After you choose what you want to do. But me, I will go with the option 2. Okay. And if you look at, and so after, of course, we had to do a bit of work, but basically the idea is to, what we found actually is there was some irregularities in the way the Tandilla height were mapped in the paleogeography from Scotties. Okay, basically the surrection was happening too late in this model. Okay, and so a way of correcting for that will be to improve on these paleogeographies to ensure that this surrection of this mountain range happens a bit earlier in the model. Okay, of course. You can find other ways of approaching the problem. and finding something that match better with the observation. Okay. Another way of looking at that is to look at the sediment flux. So here I'm looking at the Orange River and basically mapping over time the position of the Orange River mouth as Africa is moving, and looking at how much sediment is coming out of this river. Okay, and compare that with a prediction made by looking at the accumulation of sediments in the ocean. And basically looking at comparing my sediment volume from my model with the observation or estimates based on the total accumulation over time offshore of this river system. And overall, we are able to represent some of the main features of the evolution of this system, with basically a big pulse between 80 and 100 million years ago. Then something which is quite stable for a while, and then a second peak here, which is attributed to dynamic topography, okay? That also we are able to find with the model, okay? So overall, what this kind of model provides us is a way of evaluating how, basically, quantitatively, how this paleogeography and paleoclimate model are performing against known observation. But of course, we need to be aware that the observations that we've got, okay, are just partial. Okay, there is like a big bias in the observation, and not just because we haven't put some drilling cores everywhere, but also because there is a preservation bias. Okay, so there is many of the sediments that was deposited 10, 20, 100 million years ago that basically has been completely eroded and redeposited somewhere else, and people will see them as newer deposits than what they were initially in the sedimentary record. So what the model is allowing to do is basically to look at the denudation rate over time. So you can compare that, if you want, with this pinkish histogram here represent basically what we've got from the sediment record, and see and look at why there is so much difference between the two and what could be the reason for that. Okay. So what the model is basically allowing to do is to make some quantification on the evolution of paleogeography, and trying and you have the ability to look at sediment flux and stratigraphic architecture, and basically look at how your model is performing against observation, and when there is inconsistencies, can you explain them in some way? So now I'm going to move to the part 2. I don't know what time is it, and I will continue with this analogy with the human body. And if we consider that basically the surface is the living skin of our planet, then the rivers will correspond to its circulatory system. Okay, so as basically it will transfer sediments from one place to another, and in doing so, what we are going to look at is how it might have influenced the evolution of life. All right, just that. So let's start by looking at previous models that I showed you before. And here what I'm mapping is, on this side, the water fluxes, okay? And on this side, the sediment flux over the entire Phanerozoic, okay? So the markers here, they represent, in both cases, the largest rivers that flow to the ocean, okay? The size is dependent of the amount either of sediment flux that is going out in the ocean, or water flux, okay? So usually when you have a big river, you will have a big sediment flux, but it's not always the case, okay? For example, if we are on some small rivers or streams in the Andes, okay, they might be super small in terms of water flux, but because there is so much slope, you are eroding a lot of sediments. So in most cases, the largest rivers will bring a lot of sediments, but there is cases where it's not, where it's actually not true. Okay, so that's for small rivers and steep slope. but also for large rivers which are passing through an alluvial plain or a kind of depression where they will start to deposit some sediments. And so, of course, the amount of sediment that is coming out in the ocean is going to be much smaller. So what we can do from that is basically computing the amount of sediment that is eroded, okay? And the amount, and this amount we can split it into the amount which is going directly in the ocean, okay, which is represented by this circle here, and the amount which is stored on continents. And so that's this endorheic basin that we've got here in red, okay? So you've got sediment. So basically we are able to track where this eroded sediments ends up, all right? And so here you've got a view of that in a graph. So you've got in blue the total erosion, okay? Flux. In purple, you've got the amount which is directly feeding the ocean, okay? And in orange here, you've got the amount which is stored in basically the continents, okay? So you see there is like, if I just look at the blue one, there is a period here where it's relatively stable. Then after it starts to increase around the Ordovician Silurian time. Then after it stays as a plateau as well, decrease rapidly just after, you know, so during when we start to have the assembly of the Pangea, you know, it stay at the plateaus, and after it start to decrease, and then after we've got some fluxes here, which usually correspond to periods of active orogenic phases. So you start to build like a huge mountain range. So one of the things that have been puzzling scientists for a long time, I will have said centuries, but maybe not, is basically why we've got the huge diversification which happened in the ocean around, you know, Cambrian Ordovician period, and why we have to wait another 100 million years before to start seeing plants and animals actually moving to continents. Okay, and people have tried to answer that by looking either at purely tectonic driven problems, purely climatically driven problems, and basically this is something that remains a bit elusive up to today. No, I'm joking. So here I'm looking at the number of marine families, okay, which is recorded in the sedimentary based on fossil records, okay, and so I'm not going to look at the different families. I'm just going to look at the black top one here, which is basically the cumulative number of families over time. Okay, so you can see around the Cambrian we've got this explosion. Then after it plateaus, we've got a big a drop during the mass extinction during the end of the Permian. And then after there is several periods of extinction, but overall basically grows steadily from there. Okay. If I superimpose on top of that, so of course they don't have the same scale, but if I superimpose on top of that the sediment flux which is delivered to the ocean, I observe basically this kind of increase here. Then after I've got a kind of a plateau, I've got a drop which is happening just before the Permian mass extinction, and then after I see basically a steady increase with some drops as well. Okay, if I just do a correlation between the two, I've got a person correlation of 0.88. So really like strongly like correlated. So after there is two options. Okay, it's either you consider that it's a true correlation, or you consider that it's just a causality. Okay, and the argument to think that it's just a causality is easy. Basically, these families here are based on the fossil record. Where do we find fossils? Where there is sediment that has accumulated. Okay, so potentially what we see here is just a representation of where the fossil records are basically going to end up in the sedimentary record. Okay, so that will be the first idea. Okay, which is not that appealing for me. I prefer to say that I can solve something, but that will be a first. The second one will be to say that actually there is a strong correlation, okay? And that's the one I take me. But in any cases, even if it's just a causality, what are the things that we can do with this model then is basically look for additional places where we might find some fossil records based on where we expect sediment to be stored in the ocean. So in any cases, we can learn something from this model. I think I said that, that's okay. Okay, so now I've talked about the marine environment, and I mentioned this 100 million years gap. So I'm going to look now at what is happening for plant and continent diversification. So what we can do, and I think I conveyed the message earlier, is that basically the idea of these models was to be able to better represent the landforms and the complexity of the landscape, okay? So what we end up doing was trying to find a metric that we call the Tristan metric. No, joking. We call it the physiography. We called it the physiography index, which basically combine different morphometrics that characterize the landscape, okay? So by morphometrics, we will account for change in slope, change. So here the TPI is a topographic position index. Basically, it's the roughness of your landscape, okay? And we can also account for drainage system. And so we combine that together, all these variables, to create a single index that will characterize the complexity of the landscape, okay? So by complexity, I mean, if you've got a lot of landforms, if your surface is changing rapidly, it will have a high index, okay? Whereas where you've got something which is relatively flat, will be considered as something with less complexity, all right? So then, if we take the evolution, so similar to what we did before with the marine families, we can look at the plant families, okay? And so, of course, they start about like 100 million years after the diversification of the marine families. And then after you've got this kind of increase, again, like before, it's a cumulative number of families, okay? So here I've got that, and I can first superpose on top of that the total area which is covered by sediments inland, okay? So here, you remember I said I can look at the amount which is going directly in the ocean and the amount that is stored on land, okay, in continents. And so this red curve there correspond to the amount of sediment which is actually stored in continents, okay? And I can also use this variation in the physiography index, okay? And of course here I'm just looking at the average over continents. And so if I combine these two metrics together, so the amount that stay on the continents and the variability of the physiography index, I end up with this curve here, okay? And here I even beat the 0.88 correlation number that I had before. I have 0.9 correlation, okay? So what we believe, I forgot to mention before, when we were thinking of marine life and the correlation with sediment flux, what we postulated was that the amount of sediments also can be scaled with the amount of nutrients. Okay, so rivers as they come, they will bring, as well as sediments, they will bring nutrients. And this is this influx of nutrients that is basically allowing for the diversification of the marine life. Similarly, here, what we think is happening is basically up to, let's say, the Silurian to the Devonian. What you have is most of the sediments is directly feeding the ocean, okay? And you have minimal sedimentation inland. So you've got pretty much like bare rocks, okay, everywhere. You have to wait for sediments to start depositing in this continent to create a kind of a soil or layers where plants are going to be able to develop and grow over time, okay? And so our idea is that we can explain basically the diversification of, what time is it, Sabine? 6:50. Oh man, I don't have the time. 5. we can explain the evolution. So I will wrap it up here then. But basically, the idea is that we can explain both the evolution of the marine life, of the diversification of the marine life, and the diversification of plants, continental plants, by instead of just looking at climate or tectonic, by basically using surface processes, which is actually the product of these two components, okay, climate and tectonic. And what we think we have here is basically a tool that can help us understand how these physical parameters, okay, are driving the evolution of biodiversity. And more than that, what we think is that actually this physical parameters that control the biodiversification even before biotic processes. So after we have to discuss with the biologists if they agree with that. But that's what we state here, okay? And I will stop there. So we've got 10 minutes for questions.